So I asked you to take Conway's Game of Life in Java, whether it's yours or mine, and then compare it with C code with different levels of execution. Now I further did this with Python code for this comparison, which I didn't ask you to apply here. Here I did it for 100,000 iterations, and we had a minimal time one, which I used as a reference. This -03 option was C. -03 is very aggressive optimizations and potentially hazardous optimizations. There are many types of optimizations in Java that are very tempting to perform, but which could in principle be dangerous. Why is that? Well, because in C, as a language, you can manipulate C code to do all sorts of things which are pushing the boundaries and you wouldn't think that you should be allowed to do in a modern language. So for example, you can take what appears to be a pointer to a structure and turn it into a pointer to a double and write it as an array of doubles. Or you could take a pointer to a function and treat it as if it's a pointer to an int and write to it. There's many things you can do in C that are not safe. And some of those things mean that optimizations which are typically safe become non-safe when the code is behaving in bizarre enough ways. And people do write bizarre code. It was before my time, but Bill Gates was supposedly famous for his crafting code to use a minimum of memory. And one of the things they used to achieve economy in memory, they would actually reuse data structures as code. So they would have a table of cosines, for example, for this program, and in the digits of the table that were that had less precision associated, or less they were less significant digits. They were far after the decimal point. Sometimes they'd actually put a bit of code in there, so they could reuse that area for code. And the point is that to eke out the smallest memory footprint, people will sometimes do very aggressive things. For example, they will kick code out of memory and bring new code in by overwriting areas of the code that had been used earlier and where there may still be function pointers around to them. They simply won't use those, and then they'll put new code in there instead. The point is, with C, you can do all sorts of incredibly low-level things that are sometimes dangerous for optimization. They're sometimes dangerous in terms of the compiler second-guessing what you're trying to do to make it faster. And so -03 will sometimes cause bugs in your programs, but we use that as a reference because it's the fastest. And so I had an execution time on the particular machine that I ran it on of 6.6 seconds for 100,000 iterations in optimized C. Okay, this is highly optimized and dangerous, potentially C. Okay, and I called that the reference, so I gave it a sort of relative runtime of 1. And I measured other things in terms of how much slower they were compared to that. So this is 1. And if something else was, say, 2.54, the -02 optimization, still very aggressive, but less aggressive, less dangerous. This is 2.54 times slower. It takes 2.54 times as long to run that code as the highly dangerous, the dangerous but highly aggressive optimization in C. 2.54 times as long for the -02. With default optimizations only in C, with sort of standard C compilation and only very standard optimizations, 15 times slower or so than the most optimized C. Java, ain't doing too badly. 22% slower, 22% longer than -03. How could that be? How could it be that Java is only 22% longer to execute that code?
It is also optimized.
It's optimized. And it can be optimized more aggressively than C while still retaining safety, complete safety. Okay.
Because of the bytecode?
Sorry?
Because of bytecode and standardized machines?
Some of it is because of that. You don't have as much machine-specific optimization, so more issues to deal with, so you can put more effort into sort of general optimizations. But a lot of it is because the language is less dangerous. You don't actually have this issue where you can have loosey-goosey passing a conversion of pointers from one type to the other, and as a result, there's certain optimizations that you can have great confidence will be correct in Java, whereas you're not so sure in C. For example, in C, you can have pointers to local variables. Let me say that again. You have a function. And I have a variable here, A, and I'll give it, I'll have some long computation for it, right? And then I call off, foo calls off to bar, and it passes
An A pointer.
yeah, a pointer to A. Okay? And later, I refer to A. I have a loop, maybe, and here I'm referring to A in the loop. Right? So, ladies and gentlemen, what's really tempting to do here is to say, okay, well, this value of A here is going to be the same one that was assigned up here, and maybe that would allow me to, for example, easily recognize some optimization involving this value and reuse it down here. But the problem here is that maybe in this loop I'm calling off to another function called baz, okay? So what I'd like to be able to do is recognize that A doesn't change during the loop. But what's the problem? If I'm calling off in this loop to baz, what's the problem here?
Baz calls bar.
Okay. Okay, so the problem is that we have a reference to A, a pointer to A here that's escaped, meaning it's no longer under our control. It's known by other areas of the program. And maybe bar stuck it away somewhere, like in a data structure somewhere. And maybe baz is getting that pointer to A and changing it. It's writing through it every time to change A.
Maybe it's deallocating it.
Maybe it's deallocating. That would be pretty funky, especially because it's on the stack. But maybe it's writing. Maybe baz is writing to A. There's no reference to A. We're not passing baz A. But the point is that bar earlier got a pointer to A, and who knows where it stuck it? Who knows where it stored it away? And now baz, we're calling off to baz with no arguments, but it might be using that secret pointer stored away to every time change the value of A. So we can't assume anymore that A is constant here. Right? We can't assume that we're reusing the same value of A. And maybe we have some god-awful expression involving A that's recomputed every time in the loop, but we'd really like to pull it to the top of the loop. We'd like to put it out, pull it out up here, this very large expression involving A, but we can't. So we have to do it every darn time through the loop. We have to reapply it with -02 applied. -03 would probably say, probably A is not modified, pull it out. Do the computation once above the loop, We don't need to do the computation every iteration through the loop. But it could be unsafe. In Java, you don't have that issue. You can't pass a pointer to a local variable around. Nah, can't do. Now, if you have a local variable that points to or has a reference in it that points to something, and that's escaped because you pass that to something else, then you get some issues. But you don't get this sort of pointer madness possibilities that you do in C. After all, in C, you could have pointers to code, and you can write into the code, using that pointer. So, in short, C is less safe. Java is safer, and so you can perform certain optimizations which would otherwise be too dangerous to perform with the default C. And as a result, you get quite good performance, despite the Java virtual machine. How is it that the Java virtual machine, the fact that we're running atop of bytecode, isn't just killing us?
Because it's actually compiled.
It's compiling. It's called JIT, just-in-time compilation. So when you go to load the Java code, it happened before. You didn't realize it. You didn't see it in time. But when I went to run this Java code, right, ladies and gentlemen, now it just happened. All that Java code got turned into code for my particular machine, my particular architecture, my particular memory size, potentially. It got customized to my context, and then it starts running the program. And that allows the Java to run without the overhead of interpreting the bytecode, running the bytecode itself. It means the bytecode is a way to get a description of the program to your machine at the time of running, and then after that it can translate it into actual code. Now there's some trickiness there. How do you call off to jar file, for example, that's only loaded at runtime? Well, just in time it could translate that in to actual underlying assembly language code, machine code for your machine. So this 1.2 times is not too sloppy. That's pretty darn good, and a heck of a lot of work went into making that possible. Python, you're spared it this year.
Apparently Python is garbage.
Well, Python is the language, ladies and gentlemen, that you would not look to write mainline code for the core areas of your program. Python is a language used to glue things together very well. You call off to this, to that, to this other thing, and those things are optimized. Maybe they are in optimized Java code or optimized C code or what have you, but you're not actually doing the heavy lifting work generally in Python itself. Python is an integrator language. Okay, it's a language to pull things together. It allows you to create very sophisticated glueware that calls off to libraries written in other languages. And as such, it's very effective. I would note that at its current level of development, Scala for mainline core code can, in some contexts, be fairly expensive. Not nearly as bad as Python in my experience, but what you get with Scala is a lot of emphasis on parallelization, the capacity to use small memory footprints in architectures where that's key. And that can overwhelm the performance loss due to sort of small optimization changes, etc. But Python, you want to be clear that Python's not in your critical bottleneck for your code on which the performance is riding. So what this means is using the right language for the job. Using languages best suited for different areas of your program suitably, and probably having an overall program that's a mixture of languages. And if you're in web programming, that's almost a reality, right? You have a program that's composed over some server-side scripting, in one language, maybe it's PHP, or maybe it's Java struts, or maybe it's the Scala Play framework, or what have you, and then you have JavaScript, which is running in the browser. So, ladies and gentlemen, today's programs, we typically compose them out of pieces, and the core pieces, the pieces where performance is key, we end up identifying through profilers. Remember we saw that a few weeks ago? Using profilers to identify the areas of the code that are most sensitive. And we could do that because the code was divided up into functions or methods that could be easily recognized. Because of abstraction, we could do it. Abstraction barriers, you think of them at first as big barriers to performance, but in fact they allow for identification of bottlenecks, and they allow for taking areas of your program and creating them in programming languages suitable to the job for high performance, and taking other areas of your program and writing them in languages like Python, for example, which allow you to very flexibly sort of manipulate groups of more efficient code by knitting them together with code that doesn't itself have to be all that performant. Okay, so much of our modern software experience has to do with multi-language frameworks where we use the right language for the job in the right places. It's not that Python is bad, it's bad for certain things. It's not that C is bad, it's bad for certain things. It's not that Java is bad, it's bad for certain things. Or to put it more positively, they're each good for a certain type of thing. Now, there are certain languages that I wouldn't say are good or that good for many things, but I won't stride my prejudices in front of you. Okay. So, ladies and gentlemen, performance trade-offs, more than meets the eye. It's easy to go by old shibboleths that Java is an interpreted language. It's not close to the metal like C. You're going to be losing a lot of performance compared to C. Learn to question those trite platitudes. Learn to question those claims. You can actually do very, very well with modern languages, even if they are defined atop of a virtual machine, if the compilers are up to the task. Okay? A lesson with performance. Any other comments, questions about this? No? Okay. So, C, Java, less different than you'd think in terms of the performance issues. Yeah.
When we try to use abstraction, we pass points into the original program. It makes the program run slower. So what's the point to use abstraction?
Because it allows you to create programs whose structure is much better suited to describing a certain type of problem. That allows us to evolve the code more easily. It allows us to spend less time debugging it because the code isn't as complex, and we can take the time spent that would have been spent doing that to improve the underlying algorithms that really count in the program. You have to understand, and this goes back to our earlier discussion of performance. Some of you may remember it. Do you remember when we used the profilers a couple weeks back? What was one of the big findings there? Well, I won't ask you for it. One of the big findings was that a few areas of the program, a small subset of the program, is responsible for the overwhelming majority of the time it takes to execute that program. There were just a few hot spots, a few areas of the program where the performance really, really mattered the most. But most areas of the program, the things to load files in and write files out, and the things that were involved in sort of setup of data structures and parsing the command line arguments, those things were in the noise. The things that really mattered were a very small subset of the program. It could be boiled down to often maybe 4 or 5 methods for that program. And that realization allowed us to put our efforts into optimizing those key areas of the program. Because we could measure them, we could improve them. We know what we had to put our efforts into. When it comes time to using something like Aspect-J, when it comes time to use something like Python or Scala or what have you, these languages which currently do have some overhead, the promise there is not that they themselves will give us greater performance in and of themselves. It's not that, structuring things with Aspect-J will make your program go faster by itself. What it's about is making the program cleaner, more maintainable, easier to evolve, easier to debug, easier to test, easier to review. And all of that translates indirectly into time savings. The fact that you're not spending 8 hours to debug a C bug because instead you're operating in Java means that you can take that 8 hours and invest it in something else. That is an opportunity cost, ladies and gentlemen, putting it into debugging or putting it into larger number of test iterations with a lower level language. You think you're gaining something, but as you can see, first of all, the direct gain is less from something like Java here than you think. But more to the point, with something like C or a low-level language, or by trying to shoehorn something into traditional object-oriented techniques rather than using, say, an aspect-oriented technique, you're ending up spending the time in areas of the programming that, like debugging, like extra iterations of testing, that take you away from the chance to optimize. And often the optimizations are secured not because of just use of a low-level language, but rather being savvy about where the time is being taken and then improving those small areas of your program. Or taking those areas of program and using for them a different language which is performant for them. So, does Aspect-J improve our performance? Absolutely not. Does it slow our performance down? Yes, probably to a certain degree. Could it still help us arrive at a program that is more performant in the long run? Yes, if we take the time that we save because of the better software engineering involved, the better structure of our code base, and we invested that time into optimization of the high-level algorithms, the algorithms of our program that really matter, and we were to, as a result, eke performance benefits out of the core areas, that could save us time and therefore make our program more performant. So there's an issue of systems thinking there, not focusing just on the obvious low-level trade-offs, those sort of old chestnuts you'll hear that people say, well, C's closer to the metal, it must be faster. It's closer to the metal. It's faster to a degree compared to other languages, but there's certain things it sacrifices. One of the things is maintainability of a program. That time could have been put into optimization of the parts of your program that really matter. So you're likely to come out ahead time-wise by far with writing your code in Java and then optimizing it. And you can get performance, I would venture, better than C if you took the time to optimize the Java by hand as to what areas really mattered compared to C code where you didn't have time to do that because you were too caught up in debugging pointer problems. But the other thing languages like C and indeed Java and indeed Python miss out on is what these days? It's going to be a defining aspect of the careers of those who go into software development for the next 40 years, for many of them, I suspect. What is it going to be? Maybe longer than 40 years. What is it going to be?
I'm going to guess either functional programming
Yeah, multi-threading in general, explicitly exploiting, well, not necessarily explicitly, exploiting parallelism. Capturing parallelism in C is not a pleasant undertaking. Efficiently using parallel code in C. Can you do it? Absolutely. What do you sacrifice? You sacrifice time to do other things. Can you do it? Yes, you can accomplish it. But it takes a lot of time, and that time could have been spent optimizing other components of your program. Could have been spent adding new features. With Java and Python, both in and of themselves as language, there's limited built-in support for parallelism. Something like Scala is much more readily available. So I would venture that increasingly these old statements that something's close to metal and therefore faster is going to be very objectionable. Not just because the differences in raw performance are a lot smaller than you might think, but also because you are leaving behind some of the biggest gains which come in the area of concurrency and parallelism. Okay? Some comments there. Okay. So when we think about improving performance, think bigger these days than the underlying code. And these are already stripping away a lot of the benefits that would accrue for higher level languages like Java and Python at a practical domain when you think of how long it takes to create that code. Okay.